Alright folks, let's get started maybe. And yeah, maybe we can start by talking about this exercise number 5 if you have questions about anything from last week's exercise. I don't necessarily have anything I'm planning to go over, and in fact we're going to revisit some of the things from last week in the lesson for this week, so that alone might clarify some of the issues that might have come up with exercise 5. But can I ask, like, do you have questions about anything? So that could mean one of two things. Either you have questions about everything and you don't know where to start, or it was totally clear to everyone. And I suspect it's not the latter of the two, but yeah. Not necessarily. I mean, there's many different ways to do things in Python. If you chose to use pandas, for instance, instead of using NumPy, that might be a bit problematic, but frankly speaking, I guess I'd be curious to see how you did it, but if you end up getting the right solution with a different path to how you get there, it's not necessarily a problem. I mean, there's some things like if you're just copy-pasting the code 100 times to print out 100 values, okay, that's not really what we're teaching you to do here, but yeah, there are some cases when there's other solutions. The issue could be that it's possible you might not pass some of the tests in the auto grading. So if your data ends up in a slightly different format, it's possible that you might not. Like the auto grading stuff checks to see whether you get the right values that we expect from the exercise, and sometimes if you've got something different won't take a lot of time, but we're going to talk about how to interpret error messages. So basically just how to break those down and figure out, what went wrong and where to find the place to fix in your code based on the error messages. And then a little bit of stuff about how to debug your code efficiently. So some tips about, basically when you've got a bug in the code, how to find it and how to do that as quickly as possible. And then we'll actually give the preview of the exercise before we go down to join the other group, since it's a NumPy exercise, and they'll see the pandas preview. So that's what's coming up, and we're going to start here with the NumPy lesson. And if you haven't already, you can go here to the landing page, and then if you click on just the top link there, you should end up on this advanced data processing with NumPy. Advanced should maybe be in quotation marks, because I don't really think this is necessarily like advanced from the computer science perspective, but it's advanced for us, so that's good enough. And you can launch Binder, CSC notebook, something. Binder's not working. So once you're here in Jupyter Lab, there's a directory called work, and inside is a directory called notebooks. And we'll click on that. It also has a notebooks directory inside of it, and then L6, and NumPy is where we're going. So there's a few directories you've got to click through, but it's pretty much like you click on the only thing available. So I don't think you can get yourself too terribly lost. And what we're going to work on, our notebook for today, is this advanced data processing with NumPy. So if you double click on that, it should open up in Jupyter Lab. Again, if you're having problems with that, either get my attention or Lotha's attention, and we can help you out. Otherwise, I'm going to assume everybody's able to sort of see this, and we can kind of continue on from here. So what we're going to work with today is a data file. In this case, I just grabbed one from a database of weather observations in the U.S. from the U.S. Atmospheric or National Oceanographic and Atmospheric Administration's webpage. They have a huge climate database you can easily search through. If you look at problem 4 from the exercise for this week, it tells you how to search and find your own data in there. But so grab something from the state of Michigan, where I grew up when I was younger, from the airport there. And this is the data file format that we have. It's daily temperature observations, and this is the first 5 lines of the file. So it looks a little bit different than what we dealt with last week. You can see here from the dates that we're starting in 2007, first day of January. So the first 4 here are the year, 2 for the month, and then 2 numbers to indicate the day. And we've got precipitation data, average temperature, maximum temperature, and minimum temperature. This stuff is probably pretty familiar on some level already. And then we've got some stuff that we don't really need, like none of these values are changing: the latitude and longitude of the station, the elevation, and the station ID. We don't really need this stuff. So we've got 9 columns, and we're going to load this data in and have a look at it so we can see what we're working with. Like always, first thing we have to do if we're going to work with NumPy is bring it in. So we're going to import NumPy as NP. Sort of normal thing to do here. I've left in here the name of the data file because it's some weird list of numbers, but in the cell beneath where you import NumPy, we're going to read in this data file. It's just sitting here in the same directory where we're working, and we're going to read it in using the gen from text like we have before. So you remember for the gen from text, first thing we should give is the file path, or the name of the file we're going to load. In this case, we also want to skip the header. So we can add the skip header parameter. And if you look here at the preview for the file, we've got 2 lines of header material. So there's a sort of the names, and then there's also these dashes underneath. So we'll skip the top 2 lines. And because we don't want some of these other columns, we only want date, average temperature, max temperature, and min. We're going to use this use calls parameter to specify that we only want some columns. So for date, for instance, if we start counting at 0, we're going to have 0, 1, 2, 3, 4. So the 4th column, we're going to skip precipitation, so that would be column 5, and then we'll take 6, 7, and 8 for the average, max, and min temperature. So 6, 7, 8. We've done this before, right? Yep. We've got a typo here somewhere. Skip header equals 2, comma, what don't you like about that? Ah, yes. Oops. Thank you. Yeah, so there we go. I was missing my equal sign here for the use calls. And if you do a print now of what we have in data, we can see what our data looks like. And no big surprises here. First column looks like dates, at least roughly something times 10 to the 7. When we bring it in as a number, that looks like a date. There's a bunch of these minus 9999 things we'll talk about in a second. And then some temperature max and temperature minimum values that are shown in the other 2 columns. So yeah, you can see already here in the preview of the data file, there's these minus 9999 values. And that's the way that this particular data file format indicates missing data. Now, having a number in there like that is not necessarily that useful for us. So we can convert those missing values to something more useful, like an NP, not a number, NaN format. So let's do that. And the way we're going to do it is using masks like we did the last time that we dealt with this kind of issue. And we don't even need to split our data into columns to do this. We can mask everything right here in the whole data array. So we've got this, like, whatever, we didn't check the shape of this thing, but it's going to be 4 columns wide and some number of lines long. If we wanted to, we could, add a cell and just print out what data.shape is. And that shape parameter will tell us how big the array is. So in this case, it's 4,016 lines or rows and 4 columns. And yeah, we can do this kind of mask operation to the whole thing at once. So any place there's a minus 9999, we'll replace with a NaN, or not a number, in NumPy. So we can do that with DataMask. So make a new variable called DataMask, and we'll set DataMask equal to a mask array for the condition that data is less than minus 9998. There's a few different ways in which you could handle this problem of trying to convert the minus 9999 values to not a number. One of them is to basically find any place in data where you have a value that's less than minus 9998. Since we have dates and temperatures, we can be pretty sure there shouldn't be any real value in this data set that's smaller than minus 9999 or minus 9998 because there shouldn't be any, temperature doesn't go below that, and dates also shouldn't go into small numbers like that. So this is the kind of cheap and easy way to do this conversion. It's just to identify anything that's smaller than minus 9998. Alternatively, we could convert this column to integer values and check to see if a value is exactly equal to minus 9999 and do the conversion that way. It's a little extra work and doesn't necessarily do anything more useful for us, so we'll just do it this way. If you were dealing for some reason with data that actually did involve negative numbers of about this size, you wouldn't necessarily want to do this, because if you had minus 10,000 somewhere in your data, then that would also get converted to not a number when it might actually be something meaningful. So we'll make our DataMask, and I guess, do you get what's going to happen here, right? Any place that we find a value of less than this, minus 9998, it's going to get set to be true, right? And any place else, the value is going to be false. So this is going to create an array that's the same size as data of true and false values, and any place that we've got a value smaller than minus 9998 will have its value of true, and then this is going to allow us to replace these missing data values with something more useful. We can do that here by now saying that data with our data mask, so in any place that the mask value is true, we're going to replace that with np.nan. So that's the NumPy syntax for not a number. So anywhere that this condition up here is true, we'll get an np.nan in there. So you can run this cell at this point, and the expectation is all the minus 9999s should go away, and we should have nan in their place. So if we print out data, for instance, you should see in the few lines that you have displayed that we now have nan in places where we previously had minus 9999. So this is useful because you remember from last time that we dealt with this isFinite function in NumPy to check and see whether a number was a real number or whether it was something like a nan or infinite. Now we have a way to be able to remove data from some of the columns if we do have values that are missing data. So we can basically remove those observations from our data set. Okay so far? I know this is not terribly exciting, but this will come in handy for the exercise. All right, so we can do another thing we did last week already as well, and that is to split our data into different columns. I think you probably remember how to do that, but we know the first column here is called date, or, well, it's the dates, so we can call it a variable date, and that's going to be data colon, comma, 0. So we're going to take everything in the first index, so that's the rows, and then values only from the first column, column 0. And we're going to assign those to a variable called date. So this should be a list of all of our dates from our data set. We did this last week, so I guess probably you have some idea what to expect here. But if we print out date, we can indeed see that we have a one-dimensional list of all of these dates from the first day until the last day of our data set. I left these in here, these other conversions for the other variable names, so that you can just run that cell that has the t-average, t-max, t-min to split the other columns of this data into some variables that we can work with. All right, so things are read in. We've got some variable names. Now we're kind of ready to start exploring a little bit. And a useful place to start is to figure out, what is the range of dates we have. We can see this already in the preview from the printing out something like date, but if for some reason they were in an order that we didn't necessarily, if the dates were out of order for one reason or another, we could check and see when the starting date is by printing out date.min. So you might remember these methods that are built into NumPy arrays to check things like minimum value, maximum value. We can print out date.min, so that should be the minimum value in the array called date. And what you see here is 2007, January 1st. Yeah, no big surprise, we've already seen that. Same thing goes that if you print out date.max, Oops, I guess I should put in maybe some things like date. If we print out the max of date, we should expect to get the last value in our data set, and sure enough, we get 31st of December 2017. So we've got 11 years of data in this particular data set. Now, at this point, we know how many days we have, and our next sort of step in terms of data processing is to check and see how complete the data coverage is, if we've got missing values or anything like that. And we could check, for instance, the dates just to make sure that there's not any missing dates in here. So if we make something like a date mask, we can set it so that this will be true anytime we have a date that is there, that is defined. So we could say date mask equals NP, here comes the is finite. So you remember this guy from last time. Anything that's not a nan or infinite will come back as true. And, oops, not infinite, but is finite. So date mask equals np.isFinite of date. Doesn't generate any output, but if you run the cell beneath this, you should see that the number of days is 4016. So this is just counting all of the true values in the date mask array. And we're doing something we haven't done before, so we haven't seen this guy, this np.count non-zero. There's a few different ways in which you can count the values in an array. Count non-zero is one that is useful for doing things like determining how many non-zero values you have in some array. Oftentimes if you're dealing with like systems of equations, there'll be a whole bunch of non-zero values or a small number of non-zero values and a lot of zero values in the data structure you have. So this count non-zero is used for that. But it's also helpful for doing things like if you give it a mask array like we have, date mask, anything that's false will not be counted. So for instance here, we have all of these values and it says, okay, well there's 4016 of them that are true for when we do this is finite operation. So when we check in date to see if we have real values there, we get 4016 that are true. So this tells us the number of days we have in our data set. You might already remember that that was the number of lines we have when we read the data in. So in other words, it doesn't look like we have any missing data. But we can check to see if we have missing data. And we could do, for instance, a missing date mask. And for that one, we're going to do almost exactly the same thing we did before with one character different. And that's this guy, the tilde. So if you're using a Finnish keyboard, you probably never even use this thing. So in case you're wondering where it is, it's the same key that has the little hat and the like no, it's not the kaksoispiste. It's like the two dots on top of the letter, whatever that's called. And at least for me, I have to press like Alt or Option and then that key to get this tilde character to show up. I guess it's Alt
Control and then the tilde character and then space.
Yeah. So if you can't get that thing to appear, let us know. It's not a very often used character in normal everyday typing, but it does something interesting. So let's finish typing in what we have here, which is np.isFinite of date. So you can see we're doing the same thing we did before with np.isFinite, but with this tilde in front, it does the logical not operation. So anything that's true gets converted to false. This is a useful thing to do here because what we did the first time was we counted all the values we have where we did have data. If we want to know how many we don't have, that is the opposite of how many we do have So we can put this little tilde in there, and it will convert a true value to a false value, and vice versa. False would become true. Does that make some sense? So we didn't really talk about logic in much detail, and I realize now that like when we get into using NumPy, it would actually be useful to talk about logical operations a little bit, because things like the masks, there's some hidden logic in using those, and when we do this tilde character, there's the not thing that's a bit different than what we've done before. Just to make sure that you all get the general point. In the first time around, we counted up how many real values we have, and if we do the opposite of that, we get how many values that would be nan in this operation. So if you run that cell and then you run the one beneath it, what you'll see is that we have 0 dates that are missing in the number of rows we've read in the data set. That's not really a big surprise because the dates are just numbered sequentially. So whether we have data on that day is a different thing. We just have a list of all the dates that have occurred between these two starting and ending days when I pulled the data from this database. So yeah, kind of not that interesting to do this. But what's more interesting is, for instance, to do something like look at the t-average column. You saw there was a bunch of nans at the start and a bunch of nans at the bottom when we saw the preview of the data, or you can scroll up if you want to convince yourself that that's the case. You can see it, for instance, here. If we want to look at something like t-average, we can make a t-average mask. And t-average mask will be just simply NP is finite of t-average. So this will tell us how many real observations we have for the average temperature in this data set. If you put that in the line above this print statement, you can run the cell, and what you'll see is bad news. We don't have any average temperatures in this observation period. For whatever reason, this observation station stopped recording mean average temperature at least in 2007. There's nothing in the last 11 or 12 years for average temperature. There's only maximum and minimum temperatures. I don't know why, but that's what we can see here. We count up all the values in the mask, so we do the count non-zero of the t-average mask, and it sums to 0, meaning there's no true values, or in other words, they're all NaN. So we're not going to be able to work with t-average in this data set. You will experience perhaps the same thing if you work on problem 4, which is an optional problem in this exercise for this week. If you pull the data for the Sodankula station, you'll find that there's also missing t-average data. Okay, so let's go on to something that's maybe slightly familiar, but we're going to take a new spin on it, and that is dealing with calculations within a date range. So we did a little bit of this stuff last time, but before we continue here, let's just check. We're going to work with the Tmax column now, maximum temperature observed on these different dates. And the first thing we can do, since we know how to do it now, is just check to see how many missing values we have for Tmax. So we'll make a missing Tmax mask. A lot of masks so far today, but hopefully that'll get better. We'll deal with fewer of them later on. We're going to use the tilde again, and then np dot is finite of t max. So this is maybe getting a little bit redundant at this point, but we want to just check and make sure we're not missing any data. Missing tmax mask, or tmax mask equals not np is finite of tmask. So again, this should tell us how many missing values we have. If you run that cell, you should see we're missing 7 values. So that is a little bit more interesting. Now we at least know that if we're going to deal with this data, like if we want to calculate the mean, we're going to have to get rid of the missing values, because if you do something like just tmax dot mean at this stage, it's going to come back as not a number. If you have any NaN values in the variable you're trying to calculate, a minimum, maximum, mean, it always comes back as not a number. So there are functions in NumPy to avoid that, but you can convince yourself that there's basically none of these things you can do. Standard deviation, also not a number. If you mix not a number into the calculations in NumPy, you're going to get not a number back out, unless you use a special function designed to avoid that. So we've got these 7 values we got to get rid of. We'll do it the same way we did it before, and we'll make a mask of those bad values and then remove them from the data set, same as we did last week. So we had tmax is what we're working with. Tmax mask, in this case, will be the mask for that data set, and that'll be np.isFinite of tmax. So any place we have a real value, we'll keep it. Any place where there's a bad value, we're going to get a false. And this is our first step, is just to make the mask. So wherever we have missing data, we're going to have a value of false, which means that if we do something like tmax underscore clean, so the version of the tmax array where we've removed the bad values, we can simply say that that's tmax with the tmax mask in here as the range or the sort of condition that we need to meet. So this is basically a true or false array, and if we stick it in here in tmax, we should remove all the values where tmax mask is false. So this is the kind of way that we cleaned our data last week too. Now, to be consistent, it's also good to do this to the dates, because now if we remove values from the sort of list of all the temperatures of tmax, we should also remove those dates from the list of dates that we have, because otherwise the arrays are going to have different lengths and the dates are going to be out of sync with like the positions. You know, position 1 in one array might not refer to the actual value for that day. So date clean, in this case, we can say it's equal to date, and we'll use the same mask that we just used, tmax mask. Originally, these two things were the same length. We removed some values from tmax, and now what we want to do is remove the corresponding positions from the date list, so that now the dates and temperatures are still connected to one another properly. Does that make sense? What's going on there? Yeah? We did this last week, so maybe it's like, okay, yeah, we get it. But I know that dealing with the masks is not exactly a intuitive thing. So do you follow what's going on here and why we need to do this second step? Like what would happen if we didn't do this second cleaning of the dates? What would be the problem?
They would be like longer than the temperature max.
Yeah. Yeah, so like if we had a simple example, like let's say we had 3 days and 3 temperatures and the first one was not a number. If we drop that first value out of the list, now we only have 2 in the temperatures, and the first date doesn't actually correspond to the temperature it originally referred to. It's now shifted off by 1. So we basically, if we want to deal with things this way, we've got to make sure that we clean our data for whatever 2 columns we want to compare in the same way. If we wanted to do it with tmin, we would actually most likely have to make a second mask to check for the missing values in tmin, because they might not be at the same positions where they're missing for tmax. We'd then have to make another date array that has been removed the missing values from tmin. It's a bit easier to do this in pandas. because there's functions that kind of take care of this all in one step for you, so you don't see the fact that like you're removing the date values. There's this drop NA function, where you just give it some variable like tmax, and it automatically drops that row from all of the variables that were read in the data set. That's a handy thing, and if you're curious, you can check out the pandas lesson about how to do that. Depending on what you're doing, you know, there's some cases where dealing with pandas will be significantly easier. For what we're going to do in the later parts of like the Introduction to Quantitative Geology course, life is a lot easier in NumPy than it would be if we tried to do it in pandas. In fact, there's a lot of things we just can't do in pandas. So, yeah, okay with this stuff so far. Like I said, we're going to kind of push through a little bit with a longer lesson here at the start, and you know, we'll see some things that are new coming up here in just a second, like things that are going to be relevant for you for the exercise. So maybe that'll get you a little bit more interested in what's going on. But we saw before, like last time, how to calculate average values for like a range of dates. So for like a certain month, we had a way of dealing with that last time. We could do something like calculate the maximum temperature or average maximum temperature for the whole of the year of 2010. And we could do that if we did it the same way we did before. We did something like tmax 2010. We'll just make a new variable. And this is going to be the value of tmax within some range of dates. And so the first date might be that we say the date has to be greater than or equal to the year 2010, first day of the year, so 2010, and then January 01, first 01. So that's the starting point, and then we have the ampersand here, and our other condition is that date should be less than or equal to 2010 still, but now January, December 12 and 31, last day of December. That should give us all of the values of tmax that are between this starting date and this ending date. Again, you might remember this from doing it for the months of, I guess it was May and June or something in the exercise. So the syntax here is a little bit tricky. We have two conditions, so they have to be wrapped in these parentheses. But I guess, you know, what happens inside here is somewhat more clear. This essentially is making a little mask inside here. And it's kind of a shortcut where we don't name the mask that's created, but we just use it. And if we wanted then to find the mean temperature, we could then take our Tmax values for 2010 and simply do the dot mean of those values. And if you run that cell, you'll get a temperature like 60 degrees or 60.8 degrees. This is in Fahrenheit, so that's probably obvious. There's not any place on Earth that averages a temperature of 60 degrees Celsius. Maybe if we wait long enough. But. Okay, now we're going to see a different way to deal with chopping up dates. And this will be, yeah, I don't know. Maybe it'll be intuitive. Maybe it'll be a little tricky to kind of understand what's going on here, but we'll see how it goes. First, what we're going to do is we're going to convert our dates to a character string instead of using the number values that we've been using so far. And it would be tempting to say something like date clean str, or actually let's just do it like this. Let's just see what happens if we do date clean dot as type str. So this just converts our data from floating point numbers, which we have right now, to a character string. And the as type thing should look familiar from doing type conversions last time. So we do that and we get something that looks like this. which is not really what we want. This 0.0 is just totally useless. It doesn't mean anything in terms of a date. It's not like we're going to have tenths of a day or something like that. So really what we want to do here is probably convert this to an integer value first, and then convert it to a character string. If you convert straight away from a float into a character string, of course it keeps the decimal place and the first number after the decimal place in there in the character string. So that's just unnecessary characters that we don't want to have to deal with, and I'll show you why in just a second. But if we take date clean and first make an integer array of that, we can just do date clean dot as type int. Again, we saw, I think, maybe this exact kind of example when we did the conversions to integers in the last exercise or last lesson. But we're going to convert to integers first, so we'll get rid of the decimal point and the 0 after the decimal point. That should work. And if you want, you can even just copy and paste from the cell above to the one below and just change it from int here to be str. So date clean string or character string. And you also then can change out the int that is in the as type method to be str. So that'll convert that to a character string a little bit faster than typing all of that in. And if you print out then what you have for date clean str, why did I get the same thing? Right. Because this should be date clean underscore int as type. Right, we convert to an integer, we have to convert then that integer value to a character string, not the original date clean. So sorry about that. But now what you should see is the decimal point and the 0 are gone, and that's good for a reason that we'll see in just a second here. Is that okay so far? You kind of follow what's going on?
It's going a little bit too fast.
Yeah, okay. That's kind of what I was wondering.
Yeah, I'm not sure where the date clean must be going.
Yeah, so well, date clean is something we actually dealt with way back here, I think, somewhere when we did the mask for the, yeah, it was here. Above where the section for average animal temperatures, method 1, the last thing we did there after we made this Tmax mask was to then remove the bad dates that correspond to places where we had missing data for Tmax. So that's going to make an array of dates where we've just removed the bad values from Tmax. And then after that, we were basically looking at, if we want to convert this to a character string, how are we going to do that? Well, we can't just convert it straight from character string because it's a floating point value at the moment, which means that we're going to get the decimal point in there that we don't really want. That wasn't in the original data, so instead of doing it as a single operation, we have to do it in 2 steps, which is to convert to an integer and then convert to a character string. I think it is possible to do those both at the same time with as type int and then dot as type string. I think that will work. Yeah. So if you want to get, save a line, you could convert first to an integer and then convert that output to a character string just by adding another dot as type on there. But that's not really, I don't think it's very easy to read, so it's almost better to do it as 2 separate lines. It kind of gets your attention a little bit more that way. But yeah, so does everybody have these temperature or these dates converted now to something that's a character string? Yeah? So, okay. I'm tempted to take a little break, but we're going to take a break before we go join the other group. So let's see if we can do a couple more things here, and then we'll see if maybe there's just some stuff I can kind of show you quickly to help with the exercise. The idea now is that with a character string for the date, we can split out the year and the month and the day into separate variables if we want to. And there's some good reasons to do this. If we just consider the date format, we could just make some variable here called date fmt for format. The format we have is basically there's 4 characters that are the year, 2 characters that are then the month, and 2 characters that are then the day. All of the dates that we have are in this format. There's several different kinds of formats that you might encounter in reading in data, but this is what we have here. One thing that I think we might have shown a long time back but haven't dealt with lately is it's possible to use these things like the index value slicing on character strings. So we could, for instance, say that we want just the year from date fmt. And in this case, it would be a slice that corresponds to the first 4 values in date fmt. And if you run this cell, get our data so that we're working on just a single character string, we can chop out just the month if we want, just the year, just the day. I mean, if you wanted to figure out what the average temperature is in the first day of each month for some reason, you could do that. But yeah, when we do this, we just get back to y, because we're doing a slice that starts at index 0, so that would be this guy, goes up to but does not include index 4, so it means it stops here and just gives us those first 4 values back. We could do the same thing for the month. So if we said date fmt and just gave a different range, so if we start at 4 and go to 6, that's going to start at the 5th number in date fmt, so that should be this m. And it's going to go up to but not include the 7th. So that's going to be just these 2. And if you run that cell, you should see that you just get mm back. So this is our other way that we could chop things up. The reason you might want to do something like this is that you don't have to know how many days are in the month to do this. So like if you have a month like February where sometimes there's different numbers of days, depending on how you write your logic for your code and separating out the dates, you might have some issues with leap years. So being able to pull out just the month, then we have a way to identify just values that are in January or something like that, or February, and deal with processing all of those values. Did that make sense? Yeah? All right. So here's where I think this is probably our other kind of big challenging thing for today, and that is if we want to do this to an array of character strings in NumPy, we have to do something a little bit more involved than you might think. Like we can't just take something like date and say, let me make another cell here. You might be tempted to think, well, we've got date clean, and we could take all the values of date clean, and then from those values take out another subset of like 0 to 4 to get all the years of those date clean values. This is valid syntax in Python, but it doesn't give you what you want. It just gives you back the first 4 values from date clean. And if you did that for date clean str, you get basically the same thing back. It doesn't actually slice up the the individual dates. It just gives you the first 4 values from the list of dates. So that's not so helpful. So what we're going to do is something that is I don't know, we'll call it Python magic for right now, but then we'll explain what actually happens here. And we're going to do something called list comprehension in Python. It's basically shorthand for doing little for loops, and I'll show you how it works in just a second. But if we said year equals and then put some square brackets, we can put in a variable here called date now. And in date now, we're going to put 0:4. So this is a little slice of a variable called date now. We haven't defined date now yet, but we have our slice. And then we have for. So here comes the kind of for loop idea. So it's going to be for date now in date clean str. What this does is somewhat mysterious, I'm guessing. But you can see something that looks familiar here. This would basically be the construct of doing a for loop over all of the values in date clean str. Each one of those values is going to be assigned to a variable called date now. When you go through the loop, each time you click through, you change the value of date now to the next item in the list of dates that we have. And the extra magic that happens here is that by putting this date now statement within the square brackets outside of this for loop, we actually then take a slice of the first 4 values of that variable and we put them into a list. So you can take my word for it for right now that this works. I'll show you in just a second exactly how this works. But we have year as a variable. If we look at the type of the variable for year, it's a Python list. That's not a big surprise because we put something inside square brackets. It generally becomes a Python list. So if we want to convert this year into a NumPy array, we have a function to do that, and we can just say year equals np.array of year. np.array will just convert some list, if it can, into a NumPy array. It just changes the data type from list to np.array as long as it has data that it can operate on. If you give it a whole mix, because Python lists could have true or false values or numbers or other lists. I mean, you can get this thing to break and give you error messages if you try to convert some weird list. But if it's all the same data type, you can do this and then you can print out something like year. And if you print that out, you should see now that where we had dates before, we have only the year of those values now. So when we print out year, we get this. Let's take a second and see how this thing works, because you're going to use this in the exercise. It is sort of shorthand, so you do have the option if you prefer to write this out in the other way that I'll show you in a second. You can do that if it's easier for you to understand what the code is doing. But basically, what you'll see if you look at the lesson materials or in the notebook here is that this operation, this date now, where we sliced out the first 4 characters of each one of the values in date clean str, is basically the same thing as if we made an array that we called year. And actually, I should probably say that this is the same thing as if we said year equals date now of this stuff. But it's basically like we make an empty list called year. Then we have a for loop that goes over all of the values in date clean str. And in the for loop, we append to our list called year the first 4 characters. Oops, I'm missing a parentheses here too. The first 4 characters of date now. I wasn't here for the for loops lesson, but I guess you guys kind of have some idea how for loops work, right? just goes over anything that's in a list. If it's a list of numbers, it'll go through that list of numbers. Here, if we have it go over all of our date clean str values, it will take each character string of the date and go through one by one, cut out the first 4 characters, and then append it to the list of years. That'll basically do the same thing as what we did with the little shorthand notation here. If you prefer to do it that way for the exercise, that's totally fine. There's no strict requirement that you do this kind of list comprehension format. And I leave that totally up to you how you want to do it. It's more useful that you just understand what's going on. And so yeah, you're kind of free to choose. There won't be anything in the exercise that checks to see that you've done things this way. It will check, for instance, to see that you get the right years in your list of years that you should have, but it won't check how you produce that list. No. We can do basically the same thing with the months and the days. There's 2 cells that are filled in there. If you just click and run those, that'll do the same operation for month and for day. So now we have these 3 arrays where one is going to have the year, one will have the month, and one will have the day. And the first value in each one of those arrays would correspond to the first day of the year that we have in our dates. Does that make sense what happened there with the way in which we sliced up the dates? I'd be happy to explain it more if it doesn't make sense, but I don't know. I can't tell if it's not getting a very clear indication that it did or did not make any sense.
Well, for some reason I get error messages on every line I run today.
Okay, that doesn't sound good. What kind of error message is it?
For this line, it's index error, traceback, invalid index to scalar variable.
Okay, so something was calculated as a single number value, and you're trying to access something out of it like it's a list. That's usually the case. Like if you've calculated like a mean value of something, and you try to then treat it like a list, it's usually that error.
Yeah.
I don't know where. It's probably happened sometime.
Because I did the date clean dot as type in dot as type string, and then we try to use it in the date clean.
So
Here equals date now.
yeah. Here. So this was okay. This as type int, as type str. I guess, did you do this date clean str equals date clean underscore int? I guess it must exist in some way, because otherwise it would give an error message when you try to use it.
Yeah.
But because like here, all I did was just print out date clean in the format of a character string.
Yeah.
I didn't actually assign it to anything, so it's possible it was never assigned to date clean underscore str, but
Yeah, actually, like I didn't make it as like date clean str, but I changed the date clean to.
I mean, it's possible, I think there shouldn't be any problem with overwriting the date clean values with the string equivalents. So.
Now it just started working.
Okay, well that's good. So yeah, this list comprehension stuff, again, you don't necessarily need to do it, but I'm going to show you why it's useful to chop up the dates in the way in which we've done, and hopefully do this in such a way that we have a few minutes to have a little break before we go join the other group. I'd also like to at least have a moment to show you what the exercise is about. But yeah, now what we're going to do is we'll take every month in 2010 and calculate what the average temperature was for that month and store that in an array. So we'll go for January, take all the days in January, calculate the average temperature, February, calculate the average temperature, etc. And store them each time. To do this, we first have to make a place where we're going to store these values. And so we'll do that here as means. So averages, we could call it also AVG, whatever. Means 2010. Now we use this np.zeros. You might remember this guy from before. And since we know there's 12 months, we'll just do np.zeros with 12 for the length. We know how many months we're going to have in 2010. We're also going to define a variable here called index, and we're going to set index equal to 0. We don't necessarily have to do this way for what I'm about to show you, but this is probably what you're going to want to do in the exercise. So that's the reason why we're going to explicitly define a variable called index. So now we have an empty array or an array of zeros for the mean values of 2010 and this index value. As you might have guessed, if we're defining index values, that means we're going to be doing some loops, or in this case, one loop. So for, and we'll call this variable that we're going to loop with month now. And for month now in np.unique of month. You might remember that np.unique will find all the unique values in some NumPy array. If we give it an array like month, it's going to find all of the character strings like 01, 02, 03 for each one of the months, and there will be 12 of those values that will come back. So this is kind of a quick way to loop over all of the different months that we have in our data set. And trim out the fact that like the actual list of month values is quite long. So we're going to basically go over each one of the months in our for loop, and we're going to say that the means value, or the mean for that month, so means of 2010, is going to be equal to tmax clean. So remember, we took out the bad values from tmax. We don't want to deal with them. And we only want the tmax clean values when month is equal to month now. So this is maybe where it's useful to remember that we made our original list of date clean. We split that into separate year, month, and day. That's the same length as the original date clean list. So it corresponds to like the 1st of January of 2007 all the way to the last day of December in 2017. So there's something like 4,000, I don't know, 4,009 values in there. We had 4,016 to start with. We take away 7, we get 4,009 values. It's a long list. In that list, what this statement's going to do is just find all the cases where the month is equal to the month now. Now, there's an issue here because we actually have, I think, a typo in what I've put together for the lesson material, so we're going to have to fix something on the fly. What would happen if I did this as it's written here right now? What would this give me in tmax clean? Do you have any idea? Like, let's say it's the first time through this loop. And I'll tell you that month now is going to be equal to 01 as a character string. So January. What is means in this case going to give me Actually, I'll even add something here just to avoid the one problem that could come up. If we take the mean value of what this does, what list of temperatures might you expect to get if we have the condition that month equals month now? Any idea? So we have, in here we're basically creating a mask. And so for any value of Tmax, where the month column that corresponds to that temperature value is the same as month now, which is 0, 1 in this case, that's going to be included in the values we have in what we pull out of Tmask. Does that help in some way to sort of give you an idea of why there might be a problem? Maybe it helps to note what we're trying to assign this to. So this is meant to be the average temperature for each month in 2010. Yeah. No, we won't get necessarily a mix of temperatures and months, but we do have another problem. It's not a bad guess, but there's something else here that's going to be problematic. I don't want to torture you guys too much, but I am going to make you come up with this one because I think it's important that you're going to probably be thinking about exactly the same kind of thing when you're working on the exercise.
Is month type a string?
Month is a string.
So does it, I'm not sure, but does it know that it run through different indexes using only string?
The comparison's not a problem in this case. So month is going to be a character string, month now is a character string, and they will compare, no problem with that. The month will be taken care of in the loop in terms of how we're going through here. So the month is specified. There is something else we haven't specified though. No, we're okay with that. So we're trying to fill in the means for the year 2010. Is Tmax data limited to the year 2010? No. We've got data from 2007 to 2017 in Tmax. This condition will give us the data for the month of January, but it doesn't limit that to the year 2010. It gives us every January from 2007 to 2017. That's not necessarily bad. In fact, that's what you're going to want to do for one of the other problems in the exercise. But in our case, we need this, but we also need to limit the year. And in this case, we need to say that the year equals 2010 in quotation marks. That will give us the mean value for the year 2010 for the different months that we'll loop through in this for loop. The other thing we need to do in the loop is that we need to say that our index value should be increased by 1 every time we go through a month. So the first time through, in January, we're going to put our value into index 0. Then we'll increment so the index value is now 1, so that the next time we come through here, oops, I'm missing one thing here. That's probably helpful to have as well. The next time we come through, when the index value is 1 bigger, we're now going to store the mean for February in position 2 in the list of mean temperatures that we have here. So this is explained a little bit more in the exercise since we're running out of time and you guys are running out of sort of enthusiasm and energy. I'm going to kind of cut this part short here and let you take a look at the exercise because there's a list of like kind of the different things that happen here and sort of broke it down into 5 points of like why did we do this in this way. But if you run what I've typed in here, and if you've managed to type it in the same way that I have, it's not exactly been a linear process to get there, you can print out something like means of 2010. And what you should see is the average temperature for each one of the months. It's actually the average maximum temperature for each one of the months in the year 2010. They're still in Fahrenheit, but you know, that's what we're dealing with. And you know, 87 Fahrenheit, that's pretty warm. That's going to be probably more than 30 degrees, maybe 32. So average high temperatures are pretty hot in the summer in this location. Average high temperatures in the winter correspondingly, in 2010 at least, are a little bit below 0 Celsius. Maybe -1, -2, something like that. Okay, so there's a couple things that are left here. I don't know. We need a break, I think, pretty badly, and we've got to go join the other group. So maybe what I'll do is I might be able to record some of this rest of the lecture stuff and put it up as a sort of supplement video on the course page, so that we don't have to go through this now, because it's not like you're clearly not on absorb mode anymore. So for me to continue to talk isn't going to benefit anybody. But it would be good maybe to have the option of like having the explanation of how some of these other things work. So I'll see if I can find some time either this afternoon or this evening to sort of record this extra little bit of the rest of the lecture we haven't covered, so you can see that. And if there's questions that come up, then we can deal with those. There's not too many kind of totally new concepts that are left here to introduce. It's just more things that are related to specific things you'll have to do in the exercise. So it would be helpful maybe to be able to see how some of that stuff works. Are there any questions at this point? Huh. Okay. Maybe we can. Yeah.
I think if you run the for loop for like one period of time, it doesn't reset the index, so the index
Yeah.
goes up. If I like set the index back to 0, then I get error message for the for loop.
Yeah. Yeah, if you take this, you could actually cut the, you could put the index in this cell if you want. And then you should be able to run this thing over and over again without any problem. When I broke it up in the lesson, I sort of kept the index in a separate cell just because it was outside the for loop stuff. But yeah, if you have to run it more than once, it's nice actually to put that index inside the same cell.
I still get some really weird error message.
Okay.
I can show.
Yeah, I think maybe we'll do it that way. For the exercise for this week, I think maybe I can also just record a little extra thing about introducing the exercise just briefly. I mean, you can read through it and see what's there. The important thing to note right now is that the exercise link in GitHub Classroom is not yet up. There was a little bug that we caught in the exercise this morning when we were getting ready to start the lecture, and didn't want you guys getting your exercise copies that included that bug. So You can take a look at the exercise on the course page to kind of see what you have to do. In fact, that link doesn't work. Why? That should work. I don't know why it's not coming up. But you can take a look at the exercise and read through it and get a sense of what you have to do. And sometime, probably this evening, I'll make the GitHub Classroom link work so that you can then make your own copy and start working on things. For sure, you'll have it by the work session tomorrow. But I think most likely it'll be sometime this evening. I've got to go and fix a couple things with Henrik's help. So anyway, it's quite similar to the lesson we've seen, and as I mentioned, I can just give a quick kind of overview video and put that up on the course page if you want to. If you feel like, you know, you want to hear someone else read the web page to you, I can do that. So, but we need a break, and I think we're supposed to join the other group in like 10 minutes. So sorry if that's a little bit shorter break than normal. They're probably also running significantly behind, so maybe we won't be starting right back up at 11 o'clock, but it'd be good to be downstairs at 11 o'clock to try to join the other group and talk a little bit about debugging and error messages and stuff like that. Okay, so yeah, let's get some fresh air.